Hello, today we are going to talk about index laws. Realistically, with index laws, there's five index laws that we really have to be aware of. Some of them just have some additional things that, like rules that they apply to sort of specific situations. Now, all of this should be reviewed from middle school. If it's not, that's fine. We'll get there, okay? So let's just dive right in. And rather than me just showing you, here's what they are, you can get that from the textbook. Let's look at them. So the first of the index laws we need to make sure that we understand is the multiplication law. Multiplication law says that if I have a to the third power and I multiply it by a to the fifth power, then what I'm in fact going to do is I'm just going to add the indices. To see why this happens, I'm going to break this down. So a to the third power, I could write as a times a times a. Kind of back to that idea of the prime factorization idea, working our way through there. And a to the fifth power is a times a times a times a times a. If I was then to combine these or rewrite them as a single index, I would end up with, well, there's 1, 2, 3, 4, 5, 6, 7, 8 A's. So that would be a to the eighth. So what's actually happening here is we're just adding the indices together. That is something that's really, really fast and easy. And I don't think there's too much more we have to do with that. Just looking at that, 2 to the third times 2 to the, I don't want to do fifth again, because that is exactly what we just did, times 2 to the fourth. Well, if we did that, we would assume that this would turn into 2 to the 3 plus 4, or just 2 to the seventh power. Now, let's check with our calculator just to make sure. If I grab my calculator screen, and of course it's going to be right in the way of there, and I do 2 to the third, 2 to the third is 8, and 2 to the fourth, that's 16. If I do 8 times 16, I get 128. Let's see what 2 to the seventh is. It's 128. We're in business. We got it. We're pretty confident and good. All right. First rule down, no big deal. I guess there's one corollary to this, and that would be if I was to give you a problem that was like A times B. Sorry, never mind. I'm getting ahead of myself. Ignore that. Yeah, ignore that. Let's go on to the next concept. And the next idea would be working with the idea of division. Because if we can divide, if we can multiply, then obviously we can also divide indices. So the division rule says that if I have a to the fifth and I divide it by a to the sixth, then what we're going to end up doing whenever we divide indices that have the same base is we just subtract, and it works on the same exact concept. If I was to rewrite this, this is the same as a times a times a times a times a. Why did I pick 5? And that's divided by a times a times a times a times a times a. Now, whenever we divide something, so long as everything in the top is being multiplied and everything in the bottom is being multiplied, we can cancel out any duplicates. We can factor out things. We can divide things away. If I did that, I would end up getting, I've got an a on top that cancels 1 on the bottom, an a on bottom, 3, 4, 5. So what this results in is we end up with 1 over a. So that's really powerful. That's really positive. All that's happened here is we're getting this rule of a to the n divided by a to the m is the same as a to the n minus m. We just subtract them. So if we divide, we subtract indices. Again, I think that's easy enough, no big deal. Next rule is power to a power. Power to a power comes up often, and that's when we have something like, I don't know, a to the fifth, but then I take that a to the fifth and I raise it to the third power. Let's just think conceptually what that would be. Well, what that would be, if I'm raising something to a third power, that means I'm multiplying it by itself 3 times. If I multiply something by itself 3 times, now I'm just back to that multiplication rule. So I would just add them together, and that would give me a to the 15th. Okay? Now, we don't have to do that every time. Realistically, just thinking about our numbers here, how is 15 related to 3 and 5? Well, 15 is just 3 times 5. That's all that's happening here, is we're just multiplying the indices. So if I raise a power to a power, I end up just multiplying. And that's that rule that if you go to your textbook, you'll see it's going to be something like a to the m to the nth power is the same as a to the m times n. So that's the rule. Now, this is where it gets interesting. This is where those corollaries, where I went off on a tangent earlier and then I called it all back. I can get this to the point where if I have, I don't know, a to the third power divided by b to the fifth power, and I take all of that and I raise it to the fourth power. Well, I need to apply the same rules. I need to multiply the indices, but I need to do it both on the top and on the bottom. So that's where I'm going to go next. So what this is going to end up being, when we multiply like that, we end up with a to the 12th over b to the 20th. Now notice, I can't do anything further with this. My bases are different. This one on the bottom is a B base, and this one on the top is an A base. I can't do anything further. I'm just stuck there, but it is simplified. I've gotten rid of my brackets. I've simplified things. The same thing works if we're multiplying exponential terms that have different bases. So a to the fifth times b to the sixth, and I take all of that junk and I raise that to the third power, then again, I can't combine the a's and the b's. We can't combine like that, but I can get rid of the brackets just by multiplying that index through. So I would end up with a to the 15th times b to the 18th. And again, it's ugly. They're big numbers, but that's super manageable and doable. All right. Those are the first three, probably the most important three, the ones that we're going to be dealing with all the time. Got to have those down. The next ones we have are hopefully pretty simple. The next rule that we have is the zero rule. And that is, if I take any value and I raise it to the 0 power, I will always get the number 1, except for 0 itself. 0 to the 0 power is in fact 0. But actually, why don't we see what our calculator says about that? 0 to the 0 power, to the 0, oh my goodness. Why aren't we getting that right, Stoltz? Right. 0 to the 0 power, your calculator calls it undefined. Calculator's right. I don't know why I said 0. But anything else, let's just see what happens. 6 to the 0 power. 1, 0, 5, 9, 3, 6 to the 0 power. It's always 1. Got that one down. No big deal. This last one might be the new one. This might be something that's unfamiliar to some of you, but this is, again, an important rule, and that's the negative index law. Negative indices. So if I have, I don't know, let's do a to the negative 1 power. What we have to do here is we have to turn this into 2 steps. I first have to deal with that negative. And what a negative index tells me to do, a negative index always tells us take the reciprocal. So I'm going to take the reciprocal. What that means is I'm going to rewrite this as 1 over a, that's taking the reciprocal. It's originally a over 1, so I flip the fraction, turn it into 1 over a. And then I have to still deal with whatever that index is. And the index in this case is 1. So what this in fact turns into is 1 over a. So what that really looks like a lot of times is we end up with dealing with things like, I don't know, let's do a to the negative 3 power. Well, the negative tells me flip the fraction. So that would turn into 1 over a, but then I still have to deal with the fact that I'm raising it to the 3rd power. So now I need to raise it to the 3rd power. So that would turn into 1 cubed over a cubed, and 1 cubed is 1. So my final answer is going to be 1 over a cubed. Bing, bang, boom, we got it. That is a really useful power, really useful trick for us to know. We also have to recognize that we can do this with a fractional base. So if my base, instead of being a, was, I don't know, a over b, and I raise that to the negative 2 power, again, step by step, we have to deal with the negative first. So flip the fraction, take the reciprocal. The reciprocal of that would be b over a. That takes care of my negative. Now I raise it to the 2nd power, and this goes back to what we just did previously, and it would turn into b squared over a squared. And that's our solution. So flip it, deal with whatever the power is after that. I think with that, you should be just skilled enough to get on with it. So I hope that's helpful. Good luck moving forward. And this is taking a while for me to get out of. I'm going to have to